Hello, this is Jack Jackson. In this video, we're going to continue to talk about connections between calculus and probability. In this particular one, we're going to talk about the relationship between the PDF formula and the CDF formula. Talk about how we can go back and forth a little bit. Now remember, in our last video, we talked a little bit about how we can use a graphing calculator, say a TI-84, to take, whether we're given the formula for a PDF, like in this example, or the formula for a CDF, like this example here, then we could see how we could do all kinds of things. Find probabilities, inverse probabilities, find parameters like the mean and variance and so forth, and we could go with that. However, these videos were all, that particular video was set up, and these notes were set up really for a statistics class where the students didn't necessarily know any calculus. Okay, and so we're just simply let the calculator kind of do everything for us. So when we do something like this with an integral, all my probability and statistics students need to know is that that's an area calculator. Since of course the function's always above the x-axis for the, well, both the CDF and the PDF, but we'd be integrating the PDF. That's always is actually going to be an area. We don't have to worry about above and below the x-axis and positive and negative and all that stuff. So this is just simply an area calculator, and they don't have to know that it's Simpson's rule of doing it, or they don't have to know anything about formula manipulation in terms of finding derivatives and antiderivatives or fundamental theorem of calculus to do this. They just need to know that they can plug this stuff in the calculator and get an area, or at least approximation thereof. And we can see how to do this on the calculator, and it's good practice for us in calculus class as well. But those of us that know calculus know that this integral has another meaning, or at least we know more of the meaning behind it and how it works. And in fact, we can actually, there are certain places where we can use a little calculus as well. So for example, let's see one of the screens here. Whenever we do an integral like this on the calculator, then perhaps we might be able to use the fundamental theorem to get exact values rather than decimal approximations. Like there's probably a good chance this one is exactly 5.4 and not what we see here. Let's see what else. Okay, so if we're putting this in here, these numerical integrals like this are rather slow to graph. So we can get a graph of the antiderivative, which is the CDF, if we're given the formula for the PDF. So y1 is the PDF, y2 is the CDF, which is the darker line here, thicker line. But using calculus, we can find an antiderivative for this function. It's not too hard to do that, and actually put a formula in y2 for the antiderivative rather than the numerical function integrate thing in y2. That's something that people who don't know calculus couldn't do that part, but those of us who know calculus can go ahead and do that part. Or for example, down here, same thing. If we put y1 as the CDF function, which is the one that kind of comes down up here, goes up to 1 and levels off, if we find its derivative to be the PDF, you can barely see it coming up here. If we zoom in on this part of the graph, for the PDF it comes up and back down like that. And in fact, that's the PDF graph. And of course we can get that approximately using symmetric difference coefficients, in other words the numerical derivative. Again, the only thing I tell my statistics students is, hey, just remember that this is how you put it in, and you'll get a PDF graph out of it, or at least approximately a PDF graph. But those of us who knows calculus, we could actually take the derivative of this and get a formula and put that formula in y3 rather than the numerical derivative. So we can actually can do a little bit more. So we're going to continue on in this video to focus a little bit more about this relationship between the PDF and CDF, and how we can use calculus and some formula manipulation to get some exact values for certain things. So let's look at an example here. The first thing I'll look at is what's called a uniform distribution and say uniform from A to B, it's actually the PDF function is a piecewise constant function of the form 0 for x less than A, 0 for x greater than B, and between A and B it's the constant y equals 1 over B minus A. So this is three different pieces of horizontal lines, actually the two horizontal lines, because the far left and the far right pieces are both the x-axis, and then you have this little horizontal line segment between them going from A to B. Now let's prove that this is a legitimate PDF for a continuous distribution. Now we need to establish two conditions. The first condition is that the PDF must be greater than or equal to 0 for all x. That's the first condition. Well, certainly for x is less than A or greater than B, it is 0, so that's okay. And then between, since B is bigger than A, 1 over B minus A is positive, so that's certainly clear from the formula. The other thing is we need to show that the integral from negative infinity to infinity of the PDF is 1. So we integrate from negative infinity to infinity that PDF of x. We could get that's the integral from negative infinity to A of 0 plus the integral from A to B of 1 over B minus A plus the integral from B to infinity of 0. Well, when you integrate 0, you get 0. Okay, so that's just that's that. It doesn't have any effect. So we might as well just pretend the thing only exists from A to B. And that's sort of another way to think about this. So, of course, we integrate a constant, then we just get x times that constant, evaluated from B to A. And so that gives us 1 over B minus A. I'll factor that out. And then we're left with B minus A. Evaluate x at B and A. Of course, B minus A over B minus A is 1, and that's proved what we see there. Now, notice we can effectively ignore the parts of the graph where the PDF is equal to 0, and the relevant part is where we have this little line segment. And so, graphically, what we're looking at is a rectangle, basically, for the area under the curve. And the base of that rectangle has length B minus A, so its height has to have the height 1 over B minus A, so that the area is, in fact, 1. What's the CDF for this particular function? Well, you're integrating from negative infinity to x, the PDF. Well, if you're integrating 0, as long as x is less than A, you're just integrating 0, and you'll get 0. So between A and B, you've got the 0 that you get from integrating from negative infinity to A, plus just integrating from A up to x. Well, that gives us, again, it gives us an antiderivative of 1 over B minus A x, or t, let's say, and evaluate t from x, A to x. So that's x minus A times the 1 over B minus A. So that's x minus A over B minus A. Notice if you plug in A in that formula, you do get 0. So that part starts at 0. If you plug in B, you get B minus A over B minus A, which is 1, so it ends up at 1. So this is a line segment starting at 0, actually starting at A comma 0 and ending at B comma 1. So if you integrate all the way from negative infinity up to B, you get 1. So if you want to go beyond that, you get 1 plus the integral from B to x of 0 dx. Well, if you integrate 0, you get 0. So that just gives you 1 to the right of B. So let's graph this. So you see in blue the graph of the PDF, and in red the graph of the CDF. And in fact, the red and blue graphs are on top of each other here to the left of A. They're both just 0 on the x-axis. We have a discontinuity in the PDF, but the CDFs will always be continuous. It goes across here, takes a corner, goes up here, linear piece, it goes across. Of course, the slope of this line segment is the height of this curve down here, because, of course, the derivative of the red CDF graph is the blue PDF graph. The two horizontal pieces have a derivative of 0, and this linear piece has a derivative of a constant function across there. Total area here is 1, so it's B minus A wide, and it's 1 over B minus A tall. This particular one goes from 2 to 10, so it's 8 across, which means it's 1/8 tall. means this is a line with slope 1/8. One formula of this would be 1/8 times x minus a for this piece right here. Okay, let's look at a different kind of distribution, a little bit more complicated one. Let's look at a PDF for what's called an exponential distribution. An exponential distribution has the form that the PDF of x is 0 for x is less than 0, but for x is greater than or equal to 0, it's lambda times e to the minus lambda x for some positive real number, lambda. So let's show that this is a legitimate PDF. To do that, first of all, we need to see that the outputs are non-negative. Certainly, if you're less than 0 for input, we get an output of 0. That's okay. For x is greater than or equal to 0, e to any power is positive and lambda is positive, so that output is positive. So in fact, we get a perfectly fine result there that the PDF is greater than or equal to 0. The other thing we need to know is that the integral of the whole thing is 1. So if we integrate from minus infinity to infinity that PDF of x, then the part that's below 0 here, we're integrating 0, which is just 0. So really we can basically pretend that the domain is just only from 0 to infinity if we want. And that's the part that we're going to really have to integrate because the other part doesn't give us anything. No area there defined. And so if we want to integrate from 0 to infinity of this lambda e to the minus lambda x dx, to do this we need an antiderivative. We can use the fundamental theorem. So we let u be minus lambda x, du is minus lambda dx. We put this lambda with the dx and a minus, balance it with a minus out front, and we have e to the u du, and the antiderivative is e to the u, which is e to the minus lambda x. We still have this minus out front that we had there. And well, what do we get out of that? We get e to the minus lambda x, but then we have to take the limit as x goes to infinity for the top limit, and then minus e to the lambda x where x is 0. Okay, so first of all, 0 times minus lambda is 0. E to the 0 is 1. These two minuses cancel. That becomes plus 1. And this limit, since this power is lambda is positive, the minus lambda x basically gets a larger and larger power and larger and larger absolute value power, but negative means that this whole part right here is going to 0. And so we ultimately get that integral indefinite, that definite integral that is improper converges, and it converges to 1. What's the formula for the CDF? Well, this formula for the CDF of t is and it represents in reality probability that x is less than t or less than or equal to t. And that is the integral from negative infinity to t of PDF of x dx. So again, from negative infinity to 0, that integral is just 0. So that doesn't really affect us. But what we really get is just integrating from 0 to t. Again, exactly the same substitution, exactly the same antiderivative. But this time we're just going from 0 to t. And again, this one is 1. And so the formula is, if you just sort of move this around a little bit, we get 1 minus e to the minus lambda t. So we can actually find the formula for the CDF. And so if we want to say what's the probability that x is less than 5, we just put in the 5 for the t. Of course, we have to know what the particular value of lambda is, but that will give us that. So let's graph these, and let's choose lambda as 5, for example. So the CDF is just 0 over here to the left, so we really don't even need to graph that part. The interesting part is from 0 to the right, and we have an exponential function there, an exponential decay function. It's decreasing concave up with an asymptote of the x-axis. Notice it's approaching the x-axis quite quickly. By the time we even just get out here to 1, we're already pretty close. So the total area under that curve as we go out to infinity is actually just proved. That's what we proved right here. That integral is actually 1. The CDF is also 0 over here. They're on top of each other here. But then it goes from 0, 0. It increases concave down, increasing up to an asymptote of 1 as we go out to the right. if we took a particular x value here, right here, and say we did the area under the curve, so the area to the left of this vertical line under this curve, all this up here down to the x-axis, it would kind of stop here. There's no more area over here. That area would be the probability that x is less than whatever that x value is right there. And that would be the same as the y value here on this particular CDF curve. Okay, now I'm going to go back to this function that we had in our last video. Here it is up here, and we did all this stuff with using calculator technology. We didn't really use any, I mean, there's calculus involved in the calculator technology, but you didn't have to really know any calculus to use the technology. Now we're going to actually use calculus and develop some formulas. So given that PDF function formula, can we actually find the formula for the CDF? And like all CDFs, it starts at 0 and ends at 1. This one, the PDF is 0 to the left of 3 and to the right of 7. So the CDF is actually 0 to the left of 3 and 1 to the right of 7. And in between, we need to actually integrate. So from 3 to 7, we're going to integrate this formula that we have from 3 to x, 3/16 the square root of t minus 3 dt. Let's see. You let u be t minus 3, du is dt. So we have u to the 1/2. Integrate that. We go u to the 3/2 times 2/3. 2/3 times 3/16. Let's see, the 3's cancel. 2 and the 16 cancels down to 8. So you get 1/8 x minus 3 to the 3/2. If you wanted to write that with radicals, you could make it x minus 3 times the square root of x minus 3, or the square root of x minus 3 cubed. Of course, you still have the 1/8. And so we get a graph that's in 3 pieces there. And we looked at the relevant part of the graph earlier in the last video when we examined this using our calculator. And so you can see what's going on here. So the antiderivative was t minus 3 to the 3/2 times 1/8. Then we want to evaluate it from 3 to x. So we plug in the x here for the t, and we plug in the 3 there. Turns out 3 minus 3, of course, is 0, so this term actually goes away. And so you just get 1/8 x minus 3 to the 3/2. Okay? And so this is, since this is a definite integral with the variable top part, there's no plus c to mess with here. We work out, what we work out is the correct antiderivative with the correct c. In this case, I guess the correct c was 0. Okay, and also in the last video, we looked at a CDF function was given, and we did a bunch of stuff with it using our calculator technology. One of the steps was we used a numerical derivative to find approximately the PDF. Let's find the exact value of the PDF. The exact formula for that. Well, the PDF of x is the derivative of the CDF of x. So it's the derivative of this. And we can think of this as 1 plus 20 e to the negative 0.05x all to the negative 1 power. So it's like u to the negative 1. So it's negative 1u to the negative 2, then the derivative of the u. Derivative of the 1 is 0. We got the 20 e to the w. So it's e to the w times the 20 times the derivative of the w, which is a negative 0.05. Negative 0.05 times the negative out front makes a positive. 20 times 0.05. Let's see. How did I get 400 out of that? I don't see how I did that. Let's see. It should be 100. Let's fix that. Okay. 105 times 20. Yeah, that's 100. No, it's not 100. It's just 1, actually. 105 is 1/20th. Not sure where that came from at all. Must have been dividing by that instead of multiplying. All right, there we go. So the coefficient is just 1. So those cancel each other out, and the negative and negative cancel each other out. So that's just 1. Okay, so we could write it like that. This is one way we could write it. This negative 2 power could be written this way. We could do something with these negative powers here, but I'm going to leave it just like that. So there we go. There's a PDF. We could check that with our calculator and check it against the numerical derivative as well. So that gives you some examples of how we can use calculus to go back and forth between the PDF and the CDF formulas. In the next video, we're going to talk about mean, variance, standard deviation of a probability distribution and how we can use calculus to find exact values for those things as well.